that the universe is not an infinite emptiness, but a fabric. Not metaphorically, but literally. Space and time are woven into a single cloth, stretched from edge to edge of existence. We live on its surface, unaware of the threads or the seams. To us, it seems smooth, stable, eternal. But what if one day a crack appears in this fabric? It is not an explosion or a catastrophe in the usual sense. At first, everything looks ordinary. Stars shine, galaxies rotate, time moves forward. But at one point in the cosmos, geometry begins to behave strangely. Distances stop adding up. Light is delayed by fractions of a second for no apparent reason. Space seems to sag like a stretched fabric touched from within. The human mind is poorly adapted to such phenomena. We are used to thinking that between any 2 points there is always a path, and that time is an arrow flying in only one direction. But a crack in reality breaks both rules. It does not destroy the universe, it exposes its hidden structure. For the first time, it becomes clear space is not the foundation of existence, it is merely a form that a deeper reality can take. This idea was first grasped not by astronomers peering through telescopes, but physicists working with equations. General relativity showed that space-time can bend, stretch, and compress. Mass and energy do not simply exist within space, they shape it. And if it can bend, then folds are possible. And where there are folds, there can be tears. A crack in reality is the moment when familiar geometry stops working. A straight line is no longer the shortest path. Here and there can become neighbors. Time, instead of flowing, forms a whirlpool. At such a point, the universe seems to admit that its laws are not absolute, but only local. If a human were near such a crack, they would not see a hole in the usual sense. There would be no black circle or glowing portal. Space would distort subtly, almost imperceptibly. Stars around would appear stretched, their light strangely warped. Objects would seem closer than they are and farther away at the same time. It would be a deception of the senses, but not an illusion. Reality itself would have become ambiguous. It is important to understand a crack does not arise somewhere. It arises in the very structure of existence. It is not an object in the universe, but a defect in its form. It does not have to be stable or long-lived. Perhaps such cracks flare up and vanish every second, born at the quantum level, too small for us to notice. But the very possibility of their existence changes everything. If reality can crack, then it is not monolithic. And if it is not monolithic, it can be bent. Distant regions can be connected. Tunnels between worlds and epochs can be created. Wormholes do not begin with travel, but with this realization. Space is not a stage for events, but an active participant, capable of breaking, twisting, and connecting the impossible. A crack in reality is not the end of the world. It is the beginning of a question to which humanity is only just beginning to seek an answer. What a hole in the universe really is. The word whole misleads. It makes the imagination picture emptiness, an absence of matter, a void, nothingness. In everyday life, a hole means a place where something is missing. But in the universe, it is the opposite. A cosmic whole is not the absence of reality, but its most extreme form. At the deepest level, space is never truly empty. Even where there are no stars, dust, or radiation, a quantum field exists, turbulent, unstable, filled with virtual particles that appear and vanish faster than the blink of an eye. Emptiness is alive, and it is precisely in this living vacuum that deformations can arise, the ones we habitually call holes.
A black hole is the most famous example, but it is not an opening in space. It is a region where space and time are curved so strongly that all possible paths lead inward. Light does not disappear, it simply no longer escape. Reality does not end there, it becomes one way. A wormhole is a different case. It is neither a trap nor a bottomless abyss. It is a topological defect, an error in the geometry of the universe. Imagine a sheet of paper. If you fold it and pierce it with a needle, a shortcut appears between two distant points on the surface. The paper is not torn, it is merely folded. In the same way, space itself can fold within itself, forming a tunnel. In this sense, a hole is not emptiness, but connection, not destruction, but a shortcut of reality. It does not exist in space, but with space, as a special state of its form. That is why wormholes cannot be found simply by looking at them. They do not have to absorb light or glow. They may masquerade as ordinary regions of the cosmos, revealing themselves only through subtle distortions of gravity. Even more important is this: holes in the universe do not have to be large. Theory allows for the existence of microscopic tunnels, quantum wormholes that appear and disappear at Planck scales. They are far too small for a particle to pass through, let alone a human being. But their possible presence hints at something profound. Space is actually grainy, not smooth, as it seems. If we look deeper still, a hole is not an object, but a process. It is a dynamic state of space-time that can expand, contract, collapse, or stabilize. It does not have to be eternal. Most such structures, if they arise at all, die almost instantly, collapsing under their own gravity. And yet, the very fact that the mathematics of the universe allows such forms is both unsettling and inspiring. It means that distance is not absolute, that far and near may be questions of geometry, not kilometers, that the path between 2 points may run not through space, but through its fold. When we speak of holes in space, we are really speaking about the limits of our understanding, about places where intuition fails, but equations continue to work. And if one day humanity learns to create or stabilize such holes, it will mean more than a technological breakthrough. It will be an admission that reality is far more flexible than we ever dared to imagine.
The idea of wormholes was not born from fantasy. It emerged where imagination ends and only equations remain. At the beginning of the 20th century, physicists were not searching for paths through the universe. They were trying to understand what gravity truly is. And it was precisely this search that led them to one of the strangest discoveries in the history of science. In 1915, Einstein published the general theory of relativity. Space and time ceased to be a fixed stage for events. They became a flexible, dynamic entity that responds to mass and energy. Matter tells space how to curve, and space tells matter how to move. It was a radical break with classical physics and a doorway into a world where impossible forms of reality could exist. 2 decades later, Einstein, together with physicist Nathan Rosen, asked a strange question: what lies on the other side of a black hole? At the time, these objects were called gravitational collapses, and the idea itself was almost philosophical. Solving the equations, they discovered a mathematical structure in which 2 regions of space-time are connected by a kind of bridge. This object would later be called the Einstein-Rosen bridge. It is important to understand they were not trying to create a tunnel for travel. Their goal was far more modest: eliminate the singularity, a point of infinite values that shattered the elegance of the theory. The bridge looked like a neat solution. Instead of a rupture, a connection.
instead of an end, a continuation. But there was a problem. The bridge turned out to be unstable. It existed for an instant, collapsing faster than light could pass through it. It was not traversable. In the real world, such a tunnel would be a deadly trap. And for decades, the idea was shelved in the archives of theoretical physics as a beautiful but useless solution. The return came at the end of the 20th century. Physicists began to ask bolder questions. What if space-time could not only be described, but also held in a desired shape? In the 1980s and 1990s, works of Kip Thorne and his colleagues appeared, in which wormholes were first considered as potentially traversable structures, not as abstractions, but as engineering objects of the universe. Around the same time, a key idea emerged. Stabilizing a tunnel would require exotic matter, material with negative energy, capable of counteracting gravitational collapse. This sounded like pure science fiction, but quantum physics unexpectedly offered a hint. Such effects are possible, at least in the micro world. From this moment on, the wormhole ceased to be merely a solution to equations. It became a concept, a possibility, a hypothesis balanced on the edge between science and dream. And it is here that the turning point occurs. Humanity dares for the first time to think that distance is not a barrier, but a problem to be solved, that the universe can not only be observed, but edited. The birth of the idea of wormholes is not a story about travel. It is a story about intellectual courage, about the moment when physics stopped asking, "How is the world arranged?" and for the first time whispered, "What if it can be bent?" And although no tunnel has yet been found, the idea itself has already changed science. Because once humanity allowed for the possibility of such bridges, it could never again look at space as something final or immutable.
In the universe, distance seems to be the main limitation. Light takes years to cross galaxies, millennia to carry a signal from the depths of space. Even humanity's fastest probes are only slow sparks against cosmic scales. But what if distance is not a sentence, but a consequence of the shape of space itself? A wormhole is not a road laid through the cosmos. It is a bridge thrown through it. It does not shorten the path, it cancels it. 2 points separated by billions of light years can become neighbors if the space between them is folded in the right way, as if a world map suddenly folded and Rome touched Tokyo. From the point of view of mathematics, this looks almost trivial. General relativity allows solutions in which space-time connects through a throat, a narrow region linking two distant domains. The entrance and exit of such a bridge may lie in the same universe or in different ones, in the same time or in different epochs. The geometry allows it. The equations do not object. But for human perception, this is radical. We are used to the idea that a path always lies between points, that motion is a process, not a jump. A wormhole bridge shatters this logic. It offers not movement, but repositioning, not a journey, but an appearance. Imagine two lighthouses in the ocean. Normally, a ship must travel the entire distance between them, battling waves and miles. A wormhole bridge is as if a tunnel already exists underwater, instantly connecting their foundations. From the ocean's surface, nothing changes. Waves still roll. Distance seems the same. But deeper down, another route exists, hidden from view. Such bridges do not have to be symmetrical. One entrance might lie near a black hole, the other in a calm region of intergalactic space. One end could be young, the other old. And here a disturbing thought arises.
If a bridge connects not only different places in space, but different states of time, then it ceases to be just a road. It becomes a tool for rewriting cause and effect. Yet bridges between points in space do not have to be gateways for travelers. Even if no ship ever passes through them, their very existence already changes the universe. They influence gravity, the motion of stars, the propagation of light. They can be felt indirectly, through strange distortions, through effects that do not fit the familiar picture. Perhaps this is why the universe sometimes seems illogical to us. Galaxies rotate faster than they should. Light arrives not quite from where it is expected. Space behaves as if hidden shortcuts are concealed within it, paths we do not yet know, as if the map is incomplete. Bridges between points in the cosmos are a reminder. Geometry does not have to be simple. A straight line is not a law of nature, but a special case. And if the universe truly allows such hidden connections, then our ideas of far and near are merely convenient illusions created for beings who have not yet learned to see beyond the surface of form. A wormhole bridge is a challenge to intuition. It says, space is not distance, but possibility. And perhaps one day humanity will learn not to measure the path, but to choose which points of reality should touch.
We are used to thinking of space as an unchanging background, a three-dimensional stage on which the entire drama of the universe unfolds. It seems rigid in its logic, up and down, left and right, near and far. But modern physics claims something far more unsettling. Space is not a container for matter. It is an active structure, capable of deforming, stretching, and folding. To understand this, we must abandon everyday intuition. Imagine two-dimensional beings living on the surface of a sheet of paper. For them, the world is flat, and the concept of up does not exist. If the sheet is folded, two distant points on its surface become neighbors, yet the beings themselves would not notice. Their world did not tear or disappear. It simply changed shape in a dimension they cannot perceive. We are the same kind of beings, just one step higher. Our space can bend and fold in dimensions inaccessible to direct observation. General relativity does not forbid this. On the contrary, it states explicitly, the geometry of space-time depends on the distribution of energy. And that means that under certain conditions, space can not only curve, but fold back onto itself. Wormholes are extreme manifestations of this effect. They arise where space folds in such a way that a shortest path forms between distant points, not through the surrounding volume, but through space's own structure. This is not a tunnel dug through emptiness, but a crease in reality itself. It is important to understand, folding space does not require an external place. The universe does not bend into something else. It bends within itself. This breaks our familiar notions of direction and size. Inside and outside lose their meaning. What remains is topology, the way points are connected to one another. In mathematical language, this sounds dry, but the consequences are astonishing. If space can be folded, then volume does not define distance. Billions of kilometers can be separated by a microscopic throat. A journey that light would take millions of years to complete could, in principle, be replaced by an instantaneous transition if the geometry allows it. But there is a price. Any attempt to fold space requires enormous energy. Ordinary matter tends to straighten the fold, to return geometry to a stable state. It is like stretching a fabric that constantly wants to smooth itself out.
That is why stable wormholes, if they are possible at all, require exotic conditions that lie beyond familiar physics. And yet, the very possibility of folding space means that the universe is not rigid. It is plastic. Its shape is not a dogma, but the result of a balance of forces. In the early universe, when energies were unimaginably high, space could take on forms that seem impossible today. Perhaps some of those folds have survived to the present, hidden in the depths of the cosmos. Space that can be folded is not just a beautiful idea, it is a threat to our sense of reality. Because if the form of the world is changeable, then the boundaries of what is possible are far wider than we think. And then travel through space-time is not a miracle, but a consequence of the fact that the very fabric of the universe can assume the most unexpected shapes.
Wormhole versus black hole. At first glance, they look unsettlingly similar. Both wormholes and black holes distort space so strongly that familiar laws break down. Around them, light behaves strangely, time slows, and gravity becomes almost absolute. It is no surprise that imagination often confuses them. Yet, behind this outward similarity lies a fundamental difference, the difference between a trap and a road. A black hole is a dead end. It is a region where space-time is curved in such a way that all possible trajectories lead inward. Once the event horizon is crossed, the future is already fixed, not because there is nothing inside, but because the very direction of time there points only one way. Escape is impossible, not due to force, but due to geometry. A wormhole, by contrast, implies an exit. In its ideal form, the lines of space do not converge to a point, but pass through a throat, connecting two regions of reality. If a black hole is a funnel, a wormhole is a tunnel. It does not swallow everything without remainder, it redirects. The key difference lies in the structure of time. Inside a black hole, time and space effectively trade roles. Motion toward the center becomes as inevitable as motion into the future. In a wormhole, there is no such fatal distortion. Theoretically, a traveler could enter, pass through, and emerge without violating their own causality, at least in the simplest models. But there is a trap rarely discussed. Real solutions to the equations show that most wormholes are unstable. Without special conditions, their throats collapse faster than anything could pass through them. In this sense, a black hole is the more honest object. It is stable, long-lived, and confirmed by observations. A wormhole, by contrast, remains only a possibility. There is another distinction. Black holes are born naturally through the collapse of massive stars or the merger of compact objects. Wormholes, if they exist in macroscopic form, are more likely to be relics of the early universe or artificial structures. Their appearance requires conditions that ordinary astrophysics does not produce. And yet there is a subtle connection between them. Some theories suggest that a black hole and a wormhole may be different phases of the same geometry, that under certain conditions, an event horizon might conceal not a singularity, but a passage. This idea remains controversial, but it stirs the imagination. What if every black hole is a locked door? Observationally, distinguishing one from the other is extremely difficult. From the outside, a wormhole could look almost exactly like a black hole, a massive object distorting light and space. The difference appears only in the details, in how particles behave, how gravitational waves propagate, how space-time itself rings under disturbances. That is why the question, wormhole or black hole, is more than a matter of classification. It is a choice between two visions of the universe.
In one, it is filled with irreversible falls, in the other, with hidden passages. And until we look deeply enough, both possibilities remain open.
Are wormholes traversable? This question lies at the very heart of the story. Are wormholes actually traversable, or will they forever remain beautiful illusions inside equations? It is here that science stops being contemplative and begins to ask its most dangerous question: can something pass through this? The first wormhole models gave a disappointing answer. The Einstein-Rosen bridge, arising from solutions of general relativity, collapses almost instantly. Its throat pinches off faster than the speed of light. No particle, no signal, not even light could cross it before the collapse. Formally, the tunnel exists, but in practice, it is impassable. A ghost of a road, a path that closes before a single step can be taken. But physics rarely stops at the first no. By the late 19th century, a new idea emerged. What if a wormhole could be held open, not by force, but by balance? Space tends to collapse under gravity, but if there exists a form of energy capable of counteracting this tendency, the tunnel might become stable, at least in theory. This is where the concept of exotic matter appears. It is not matter in the usual sense, but a state of a field with negative energy density. It behaves opposite to ordinary matter. Instead of attracting, it repels. Near the throat of a wormhole, such matter could act like a spacer, preventing space from snapping shut. It sounds like pure science fiction, but quantum physics unexpectedly offers a clue. Effects such as the Casimir effect show that negative energy is possible, even if only on microscopic scales. This does not mean we can collect it in a container or use it at will, but it does mean that the idea itself is not forbidden by the laws of nature. Even if a tunnel were stabilized, other dangers would remain. A traveler attempting to pass through would encounter extreme gravitational gradients, intense radiation, and violent quantum fluctuations. The slightest instability could turn the passage into a deadly trap. Traversability is not just, is there a passage, but can anything survive the transition? And there is an even deeper problem. Some calculations suggest that as soon as information tries to pass through a wormhole, it may destabilize the tunnel itself. Causality seems to resist. The universe may be protecting itself from paths that are too short, preventing logical paradoxes from arising. And yet, there is no strict prohibition. No fundamental equation states unequivocally impossible. There is only extraordinarily difficult, unstable, far beyond our technology. And the history of science teaches us that such words are often temporary. The traversability of wormholes is not a question of engineering, it is a question of principle. If the answer ever becomes yes, it will mean that distance has ceased to be a fundamental property of the world, that the universe allows direct connections between far-flung regions, and then the very concept of travel would change forever. For now, wormholes remain on the boundary of the possible, not a closed door, but not an open one either, more like an outline on the wall of reality where the handle has yet to be drawn. Every attempt to make a wormhole traversable runs into the same obstacle. Space does not want to stay open. Gravity tries to pinch the tunnel's throat shut to return geometry to a stable state. To resist this, something is required that behaves opposite to all familiar forms of matter. This is how exotic matter appears in theory, one of the strangest and most controversial concepts in modern physics. Exotic matter is not an alien metal or a mysterious substance from science fiction.
It is a state of a field with negative energy density and negative pressure. Put simply, such matter does not pull space inward, it pushes it outward. Where ordinary matter bends the fabric of the universe inward, exotic matter pushes it outward, holding the passage open. This sounds like a direct violation of common sense. In everyday experience, energy is always positive. Mass is mass, pressure presses, gravity attracts. But on the quantum level, the universe is far less intuitive. The vacuum is not empty, and energy can be less than zero, at least relative to the vacuum state. The most famous example is the Casimir effect. When two perfectly conducting plates are placed extremely close together, a region of reduced vacuum energy appears between them. This is a real, experimentally measured effect. It is tiny, but fundamentally important. Negative energy is possible. Physics does not forbid its existence. Here, however, disappointment begins. The amounts of negative energy we can produce are vanishingly small. To stabilize a macroscopic wormhole would require quantities of exotic matter comparable to the mass of a star, but with the opposite sign. Current theories offer no known way to create or maintain such states on the required scales. Moreover, there are so-called quantum inequalities. They limit how much negative energy can exist and for how long. The universe seems to impose safety locks, preventing exotic effects from getting out of control. It looks as if the laws of nature actively protect themselves against stable tunnels. And yet, exotic matter is not dismissed as a myth. It remains theoretically allowed. Perhaps in the early universe, under extreme energies and densities, such states arose naturally. Perhaps some wormholes, if they exist, are held open not by unknown substances, but by still undiscovered properties of the vacuum or dark energy. That is why the real question is not, does exotic matter exist, but how deeply do we understand emptiness? What we call the vacuum may be the most complex object in the universe. And if stable negative energies are hidden within its structure, then the key to wormholes lies not in distant technologies, but in the very foundation of reality. Exotic matter is the boundary between impossible and not yet understood, and on which side it ultimately falls will determine whether wormholes remain a beautiful idea or one day become real gateways through space and time.
We are used to thinking of time as a river. It flows from the past into the future, never stopping, never looking back. We can remember yesterday, but we can never return to it. This sense is so natural that it feels like a fundamental property of the universe itself. But the physics of wormholes forces us to question it. What if time is not a flow, but a direction, one that can be changed? In general relativity, time is not a separate entity. It is interwoven with space into a single four-dimensional whole. And if space can bend and fold, why should time remain a straight line? Mathematics allows scenarios in which the temporal axis tilts, loops, or connects to another point in history. In this context, a wormhole ceases to be merely a spatial tunnel. If its mouths move relative to each other or exist in different gravitational conditions, a time shift arises between them. One mouth may age faster than the other. The tunnel then connects not only different places, but different moments in time. Imagine the two ends of a wormhole as clocks. One is placed near a massive object where time runs more slowly. The other remains in a calm region of space. Over time, their readings diverge, yet the tunnel preserves the connection between them. Passing through it, one could emerge in the past or the future relative to the point of entry, not because time has broken, but because geometry has allowed a shortcut around its usual course. Here, the most disturbing idea appears.
Wormholes as time machines. Not fantastical devices with buttons and dials, but natural consequences of curved space-time. Theory permits closed time-like curves, trajectories along which an object can return to its own past. But at this point, the universe seems to push back. Causality paradoxes, the grandfather paradox, self-creating events, are not mere logical games. They threaten the very structure of physical law. Many physicists, therefore, believe that mechanisms exist to prevent such scenarios. Stephen Hawking called this the chronology protection conjecture, a hypothetical principle that forbids travel into the past. The possible protective mechanisms are varied: quantum fluctuations that destroy the tunnel when a time loop is about to form, energy densities that grow without bound, instabilities that make passage impossible. None of these has been proven definitively, but their presence feels almost deliberate. And yet, the fact remains, the equations do not forbid time from being a direction rather than a destiny. They allow forward and backward to be matters of trajectory through space-time. And if wormholes ever become traversable, humanity will face not just new routes, but the need to rethink the very notion of cause and effect. In this sense, time is not a wall, but a slope. Usually we move downhill without choice. Wormholes hint that under certain conditions, one might move along that slope differently. And the real question is not whether physics allows it, but whether reality itself could withstand it.
Travel through a wormhole changes not only distances, but the very notion of cause and effect. In the ordinary world, every event has its place in time. Yesterday gives birth to today, and today creates tomorrow. But if the entrance and exit of a tunnel lie at different temporal coordinates, this logic collapses. We enter the territory of closed time-like curves, loops of causality. What is a causality loop? Imagine a signal sent through a wormhole that returns to the past. Its presence there becomes the reason the signal was sent in the first place. Accidentally, deliberately, or by an observer's choice, the structure of events becomes self-sustaining. At first glance, this feels like magic. An event creates itself without any external cause. This is where the famous paradoxes arise. The classic example is the grandfather paradox. A traveler goes back in time and prevents their grandparents from meeting. Then the traveler would never be born and therefore could not have traveled back in the first place. Taken literally, a closed causality loop destroys the logic of cause and consequence. Physicists search for ways to avoid these paradoxes. One solution is the many worlds interpretation. Every change to the past creates a new branch of reality. The paradox disappears because the traveler's actions do not alter their original world, but generate an alternate timeline. The tunnel does not violate causality, it merely opens a passage between parallel universes. Another option is Kip Thorne's self-consistency principle. It states that any causality loop must be internally consistent. Any action taken in the past is already accounted for in the future. No grandfather is killed because events inevitably arrange themselves to avoid contradiction. But these solutions remain theoretical. There are no experimental tests, and it is unknown how quantum fluctuations, gravitational waves, or space-time instabilities would affect real loops. Any attempt to pass through a tunnel into the past might destroy the tunnel itself, trigger an energy burst, or produce entirely unknown effects. Causality loops force us to rethink familiar ideas. In a wormhole world, effect is no longer a simple continuation of cause. Time becomes a fabric that can be twisted and folded. And although the universe may protect itself from logical violations, the mere possibility of such scenarios reshapes our understanding of reality.
Ultimately, causality loops are not just mathematical curiosities. They are a boundary where physics, philosophy, and imagination intersect. Here, humanity first realizes that travel through space is not only about distance, it is about the flow of time itself, and therefore about our deepest understanding of causality, destiny, and choice.
When we talk about wormholes, most people think of cosmic portals between stars and galaxies. But in reality, these structures are capable of far more. They could potentially serve as time machines. And not in the science fiction sense of press a button and appear in the past, but as a direct consequence of space-time geometry. In ordinary physics, time travel seems impossible. We move forward along the arrow of time, and going backward appears logically forbidden. Yet within the framework of general relativity, space and time form a single whole. If space can bend, twist, and connect, why shouldn't the direction of time be altered as well? Inside a wormhole, time ceases to be linear. Imagine a tunnel, one end near a massive star where time slows due to gravity, and the other in a relatively calm region of space. Because of the difference in time flow, the two ends of the tunnel can become offset relative to each other. The entrance could lie in the past and the exit in the future, or vice versa. Theoretically, passing through the tunnel could place you at a moment that, for an outside observer, precedes your entry. Here, theory intersects with famous paradoxes. Any interference with the past could create logical contradictions, but as discussed before, there are possible solutions: multiple universes, or Kip Thorne's self-consistency principle, which ensures that events in a causality loop are compatible with their own future. In both cases, a wormhole stops being just a portal through space; it becomes a bridge through time. Thorne and his colleagues showed that stabilizing such tunnels requires exotic matter with negative energy. It does more than keep the wormhole throat open. It can prevent the tunnel from collapsing when an attempt is made to traverse it through time. Without it, the tunnel would collapse, and any attempt at time travel would end in catastrophe. It is important to emphasize, wormholes do not violate the laws of physics. They do not break causality. Rather, they create alternative geometric possibilities hidden in the structure of space-time itself. This is not a fantasy about time travel. It is a direct consequence of relativity and quantum physics. Theoretically, such structures can exist, which is why they are so fascinating to both scientists and writers. In practice, humanity is far from creating such a tunnel. The energy and technological requirements exceed current capabilities. Not only would exotic matter be needed, but also control over space-time on scales comparable to a solar system. Yet the concept of a wormhole as a time machine challenges our very notion of travel. In ordinary life, a journey is limited by distance. In the world of wormholes, distance ceases to be an obstacle, and a new dimension, time, is added. Travel becomes not only about where, but also when. Wormholes as time machines are the boundary of the possible, where mathematics meets philosophy. Here, humanity first confronts the question: if one can alter the past or arrive in the future, how does that affect our understanding of freedom, fate, and responsibility? And although we remain at the theoretical stage, the mere possibility of such tunnels opens an infinite horizon for imagination and future discovery.
Dangers of traveling through space-time. The idea of wormholes as portals through space and time is mesmerizing, but it conceals invisible and deadly hazards. Even if a wormhole were stable and traversable, that does not mean a journey through it would be safe. Space-time is not a gentle path through a park. It is a turbulent ocean where every movement can be fatal. The first and most obvious danger is gravitational forces. The throat of a wormhole connects regions with vastly different space-time curvatures. Near the entrance, gravity might feel almost normal, but the deeper you go, the more extreme the distortion. Any object, a human or a spaceship, is subjected to intense tidal forces. Stretching and compressing can elongate a body or crush it to atoms. Physics here shows no mercy. The next threat is radiation and energy bursts. Space around the tunnel is not merely distorted, it is filled with energetic fluxes arising from field curvature and vacuum interactions. Quantum fluctuations generate powerful gamma and X-ray bursts. Any traveler would be under constant bombardment by invisible forces capable of instantly destroying living tissue or electronics. Equally dangerous are instabilities of the tunnel itself. Even a slight disturbance near the entrance could trigger a collapse of the throat. In theory, exotic matter should hold the wormhole open, but its distribution is extremely sensitive. The slightest mass shift, energy impulse, or even the passage of particles could cause instant collapse. For a traveler, this makes passing through the tunnel a deadly gamble. Time differences between the entrance and exit add another layer of risk. Emerging in the future or the past exposes organisms and equipment to altered physical conditions. Particle decay rates may accelerate or slow down. For biological systems, this could induce fatal stress. For technology, catastrophic failure. There are also quantum effects. Chaotic field fluctuations may appear in the tunnel's throat, creating microscopic tears in spacetime. On a macroscopic scale, this could manifest as sudden disappearance of objects, abrupt changes in trajectory, or even temporal distortions. Travel becomes a roulette where no outcome is guaranteed. Yet the most fundamental danger is causality violation. If the tunnel connects different points in time, any action in the past can trigger an unpredictable chain of events. Attempts to fix a mistake or interfere could collapse not only the wormhole, but the local structure of reality. Effects might be local, destruction of matter near the entrance, or global, including distortions of physical laws at a distance. All of this makes wormholes not just an engineering challenge, but a trial for life itself. A theoretically possible journey through a tunnel is not a stroll, but an extreme experiment with the very fabric of the universe. And it is precisely these dangers that make the subject so compelling for science and fiction alike. Behind the beauty of the portal lies immense risk, where the boundary of the possible intersects with the boundary of the lethal. A wormhole is a bridge offering the chance to instantly traverse space and time. But behind every such bridge lies chaos from which there may be no return. Any attempt to use it becomes a test at the limits of physics, biology, and logic.
The appearance of a wormhole. If a wormhole existed near us, we would not see it like we see stars or planets. It does not sparkle, glow, or breathe in any familiar sense. Its presence does not manifest through volume or shape, but through distortions of the surrounding space itself. Yet approaching such an entrance would leave no observer indifferent. It would be simultaneously mesmerizing and unsettling. The first thing one would notice is that light around the tunnel behaves strangely. Stars, galaxies, dust, and cosmic radiation appear stretched, warped, as if reflected in water. Rays of light passing near the throat bend, creating the illusion of a mirrored vortex. Space seems to pull toward a point where no visible object exists, and at the same time it appears to vanish, forming a void with a sparkling contour. Through a telescope, one might notice an extreme gravitational lensing effect. Near a normal massive star, lensing slightly distorts background objects, gently shifting their apparent positions. With a wormhole, the distortions are anything but subtle. Objects stretch into rings, spirals, and fantastical shapes, warping more as they approach the entrance.
Space seems as if it is trying to draw the eye inward. For the human eye, at close range, the effect would be even stranger. Familiar reference points lose their usual proportions. Distant stars may seem closer, and features on planetary surfaces appear displaced. Moving around the entrance gives the impression that space itself is breathing. Walls shift, light bends, horizons fracture, and the brain cannot interpret what the eyes perceive. Even more dramatic phenomena are possible. If the entrance connects regions with different temporal coordinates, an observer could witness past and future moving simultaneously. Comets from millions of years ago appear next to stars not yet born. Time seems to overlay space, producing an invisible kaleidoscope where past and future dance together. There are no tactile sensations when approaching a wormhole, yet the physical environment hints at its presence. Gravity becomes variable. Steps may feel lighter or heavier, as if the ground beneath shifts density. Every movement is accompanied by a subtle trembling of space that cannot be explained by ordinary physics. The most mysterious aspect remains the invisible entrance. At first glance, it may seem entirely absent. It emits no light, has no edge, and does not stand out. Its presence is felt only through distortions of light, gravity, and particle motion. It is not a portal in a conventional sense. It is a folded section of the universe's fabric, pulling both gaze and intuition inward, promising an impossible journey hidden behind apparent emptiness. Thus, a wormhole's entrance is both a visual and psychological phenomenon. It beckons and terrifies, stimulates the imagination, and confounds the mind. It is the moment when a person first realizes that space can be more than a measurement. It is a living, dynamic entity, ready to open a path to places where ordinary physics and ordinary eyes cannot follow.
Indirect signs of a wormhole in space. If a wormhole exists in the cosmos, it cannot be seen directly. It does not glow, emit radio waves, or produce any familiar visual signature. Yet it can leave subtle, indirect traces, signals from nowhere, anomalies in the behavior of light, particles, and gravity that cannot be explained by ordinary astrophysics. The first and most obvious sign is anomalies in gravitational lensing. Normally, massive objects like stars or black holes bend the light of background galaxies, creating arcs or rings. Near a wormhole, the effect is far stronger and stranger. Light lines warp into unusual spirals, background objects stretch and shift, and the apparent arrangement of stars seems chaotic. An astronomer observing through a telescope might notice something is wrong here, yet the exact point cannot be identified. Another signal comes from timing anomalies of light arrival. Light passing through the tunnel may appear at unexpected moments. Background objects may blink earlier than expected or delay their light by milliseconds or even seconds. These anomalies are tiny, detectable only with ultra-precise instruments, but they hint that space here behaves unusually. More extreme effects include abnormal movements of cosmic particles and gas. Tiny particles passing near the wormhole's throat change trajectory, accelerate or decelerate for no apparent reason. Observatories record these fluctuations as signals from nowhere, bursts not linked to any known source. Finally, theory predicts unique gravitational waves. Near a stabilized wormhole, the fabric of space-time vibrates in a distinctive manner. If a cosmic detector registers a non-standard wave that does not originate from colliding black holes or neutron stars, it could hint at the presence of a tunnel. The wave seems to emerge from empty space, as if space-time itself whispers its secret. All these signals share a common trait.
They are incomplete and strange. They do not reveal the tunnel itself, but only its influence on the surroundings, like seeing the shadow of an object that does not physically exist. Astronomers label such observations as anomalous, yet each detection opens a new door to a new interpretation of the cosmos. Sometimes it seems that wormholes act like invisible conductors. They create no noise, but manipulate light, particles, and gravity so subtly that conventional observation captures only hints. Their presence is felt as an invisible tension in the universe, as if the fabric of reality trembles and writhes, signaling something unusual is here. These signals from nowhere make wormholes more than a theoretical puzzle. They turn abstract equations into observable phenomena, where science and intuition meet at the edge of the possible. For those able to recognize these subtle signs, the universe ceases to be static. It becomes living, pliable, semi-permeable, ready to open a path to places where ordinary laws cannot reach.
Wormholes and dark matter. Dark matter remains one of the greatest mysteries in modern astrophysics. It neither shines, emits radio waves, nor absorbs light like ordinary matter. Yet its presence is felt everywhere. Galaxies rotate faster than their visible mass allows. Cosmic structures form differently than expected from normal gravity, and large-scale motions of matter often defy predictions. This raises an intriguing possibility. Could some of these anomalies be explained by wormholes hidden deep in space? A wormhole is more than just a tunnel. It is a distortion of space-time. It bends light, affects the motion of stars and particles, and creates localized gravitational anomalies. On the scale of a galaxy or cluster, even a small wormhole could act as an invisible conductor, subtly redirecting the trajectories of objects as if an unseen mass were present. To an observer, this effect could appear exactly like dark matter. Gravity is present, but the source remains unseen. Furthermore, theory suggests that wormholes could have formed in the early universe alongside the large-scale structure of cosmic matter. If some survived billions of years, they could be distributed across galactic clusters and the cosmic web. Their influence on light and matter would be subtle, almost undetectable directly, yet strong enough to account for part of the observed invisible mass effect. The energy properties of a wormhole also play a role. Near its throat, space-time curvature is unusual, producing gravitational attraction or repulsion that does not behave like ordinary matter. Stars may accelerate or decelerate, light may bend in unexpected ways. It appears as if a concentrated mass exists, but in reality there may be no mass at all, only the topology and energy of the field. Interestingly, such tunnels could also connect to dark energy. If wormholes can hold exotic matter with negative energy density, they become not just conduits, but stress points in the cosmic fabric, creating local variations in the rate of cosmic expansion. These effects could mimic phenomena usually attributed to dark energy. Of course, this remains a hypothesis. The existence of macroscopic wormholes has not been confirmed. Yet the idea that some dark matter anomalies might be the result of hidden tunnels opens new avenues of thought. Perhaps the cosmos is full of invisible bridges that shape the structure of the universe, guide the motion of stars, and create the illusion of unseen mass. In this sense, wormholes and dark matter are connected concepts. Both alter space and motion, both are difficult to observe directly, and both challenge our understanding of reality. If one day we can detect or stabilize such tunnels, part of the dark matter mystery might vanish, along with the realization that the universe is far more flexible and dynamic than we have imagined. The future of humanity through wormholes.
If wormholes ever move from mathematical speculation to reality, they would fundamentally transform everything we know about travel, technology, and humanity's place in the universe. These portals do more than shorten distances. They redefine the very concepts of time, space, and civilization's possibilities. Imagine a tunnel connecting Earth to a distant star cluster millions of light years away. Today, even the fastest spacecraft would take millions of years to reach it. Tomorrow, with a wormhole, that journey could be instantaneous. Cosmic scales shift. Galaxies are no longer unreachable, and humanity's expansion beyond the solar system becomes almost immediate. But with this capability come new challenges. A wormhole is not merely a road. It interferes with the fabric of reality, and any use may have unpredictable consequences. Traveling through it in time opens the risk of altering events, creating paradoxes, or violating causality. Humanity would face a dilemma: how to wield technology that can expand possibilities or potentially destroy history itself. The economic and scientific impact would be enormous. Instant travel would grant access to distant planets and asteroid resources, accelerate exoplanet exploration, and even allow real-time observation of stellar and galactic evolution. Entirely new sciences would emerge at the intersection of physics, biology, ethics, and psychology, learning to navigate multi-dimensional spaces and alternate temporal lines. Socially, wormholes would redefine boundaries. Political and cultural divisions might lose significance if any corner of the universe becomes instantly reachable. Yet new conflicts would arise. Control over wormholes, their technology, and energy could become the most critical resources in human history. The ability to move people and information instantly could create unprecedented forms of power and dependency. Ethical questions would grow even more complex. If a tunnel allows influence over the past or future, who decides how it is used? How can paradoxes or abuses be prevented? Would humanity be ready to shoulder responsibility for a reality now open to manipulation? Nevertheless, wormholes offer an unparalleled opportunity to expand civilization's horizons, not just geographically, but conceptually. They open the possibility of living in a world where distance and time are no longer limitations, where contact with other forms of life or observation of distant events becomes a practical reality rather than a dream. Ultimately, humanity's future through the lens of wormholes is a world of both possibility and responsibility. Every step through a tunnel would be a step along the edge of science, philosophy, and ethics. Whether this technology becomes salvation or catastrophe will depend entirely on how prepared humanity is to understand and respect the profound laws it would engage.
Creating a wormhole is not just an engineering challenge, it is an attempt to manipulate the very fabric of the universe. If today humanity can build bridges and rockets, tomorrow, mastering wormholes, it will have to construct space-time itself. And this is what makes the problem both thrilling and almost incomprehensible. First requirement: immense energy. To fold space and connect two distant points, forces comparable to the energy of an entire star or even billions of suns are needed. Any local energy source available to humanity today pales in comparison. Theoretically, proposals suggest using black holes, neutron stars, or massive concentrations of dark energy as anchors to bend space. Second key element: exotic matter with negative energy density. This is what could keep the tunnel open, preventing it from collapsing and stabilizing the throat. Calculations indicate that an enormous amount of such matter would be required, and humanity currently cannot produce it on a macroscopic scale.
However, experiments with the Casimir effect and quantum fluctuations give hope. Nature allows negative energy, and it might one day be scalable. Third obstacle: ultra-precise control of space-time geometry. Even the slightest deviation or mass imbalance could destroy the tunnel. This requires technology capable of maintaining the field in a near-perfect state, regulating pressure, energy, and the distribution of exotic matter down to quantum scales. An error of a millimeter or a microsecond, and the tunnel vanishes. Fourth aspect: protection from instabilities and quantum fluctuations. Even if the tunnel is created, micro-variations in the vacuum, particle fluxes, or radiation could trigger collapse. This necessitates active control, continuous monitoring, and real-time adjustment of the tunnel's state. Theoretically, it resembles the work of a highly sophisticated stabilizer, simultaneously controlling the entire geometry of space inside the tunnel. Fifth aspect: traveler safety. Passing through the tunnel involves extreme tidal forces, radiation, and time distortions. Any project must ensure protection for humans and equipment, including gravitational compensation systems, radiation shielding, and stabilization of movement inside the throat. Finally, energy infrastructure and scale. Any attempt to create a tunnel requires resources humanity cannot yet provide. It could be a global-scale project, harnessing the energy of multiple planets, colossal solar arrays, or even capturing the rotational energy of black holes. Thus, the technology to create wormholes is a mix of theory, engineering, quantum physics, and cosmic scale challenges. Today, it is a pure hypothesis, tomorrow a theoretical goal, and in the distant future, perhaps a tool capable of altering the fate of humanity.
Ethics and responsibility for traveling through wormholes. If wormholes ever become a reality, they will open not only cosmic horizons, but also moral dilemmas of unprecedented scale. A technology capable of instantly connecting distant points in the universe or altering the flow of time creates new responsibilities that humanity has not yet learned to define. First question: control and access. Who will have the right to use wormholes? Will it be a single organization, an international community, a corporation, or an individual nation? The issue is not just about resources, but consequences. Any careless use of a wormhole could affect millions of people, or even other civilizations if they exist. Control over a door to the universe is a power beyond anything humanity has ever known. Second aspect: impact on cause and effect. Time travel through wormholes can create paradoxes. Even if the many worlds theory or the principle of self-consistency resolves them, logically, the moral responsibility for the consequences remains human. Any interference in the past could alter the lives of millions or even billions of beings. The question arises, do we have the right to intervene in history, even on the scale of a single tunnel? Third aspect: ecological and cosmic consequences. Every wormhole affects the structure of space-time, creating local gravitational anomalies and distorting the motion of particles and energy. Repeated experiments could have unpredictable effects, such as disrupting planetary orbits or other cosmic structures. These consequences may not be immediately noticeable, but their scale could exceed anything humanity has encountered before. Fourth aspect: social justice. If wormholes allow instantaneous movement of people, resources, and information, this creates enormous inequality. Those controlling the tunnels gain access to universal wealth and knowledge, while others remain in the old world.
Ethics demands principles to ensure that new technologies do not become tools of exploitation or discrimination. Fifth aspect, psychological and philosophical effects. Humanity is accustomed to linear time and geographic limitations. The possibility of traveling through wormholes changes the perception of space, time, and one's own life. There is a risk of cultural and psychological shock. People may lose the sense of event sequence, personal responsibility, or the significance of their own actions. Finally, responsibility to the universe itself. If space-time is living, dynamic, and malleable, any human intervention may be dangerous not only to us, but also to the very structure of the universe. A wormhole is not only a tool, but also a test of a civilization's maturity. Ethics of traveling through wormholes requires a combination of scientific knowledge, philosophical insight, and moral maturity. This is a technology where mistakes are unforgivable and consequences can be cosmic. Before building the first tunnels, humanity must answer the question, are we ready not just for travel, but for responsibility for the very fabric of reality?
Detecting wormholes, signs in the fabric of space-time. Although wormholes remain a theoretical concept, scientists are already exploring how they might be detected. There's no direct way to see a wormhole. It doesn't emit light, have conventional mass, or leave visible traces. However, indirect clues may signal its presence in the fabric of space-time. 1. Gravitational lensing anomalies. Traditional massive objects like stars or galaxies bend background light, creating arcs and rings. A wormhole acts similarly, but in far stranger ways. Light from background objects might stretch into spirals, bend unpredictably, or appear where it shouldn't. Detecting such unusual patterns of distorted light could be the first hint of a wormhole's existence. 2. Unexplained temporal anomalies. Signals passing through a wormhole may arrive earlier or later than expected. Astronomers sometimes record flashes from stars or other objects with no apparent cause. These subtle shifts in timing could indicate geometric distortions through which light travels, directly bypassing vast distances. 3. Unusual gravitational waves. Even small wormholes can induce ripples in space-time different from those caused by black hole or neutron star collisions. Detectors like LIGO or Virgo could detect waves emerging from nowhere, indicating distortions in the structure of space itself. Such waves have no conventional source, but arise from the wormhole's influence on space-time. 4. Anomalous particle and gas motion. Tiny particles and interstellar gas near a wormhole may change trajectory without an observable force. Dust clouds can accelerate, slow down, or veer unexpectedly. These effects appear as local jumps or loops in matter movement, inexplicable by known physical laws. 5. Indirect traces via dark matter and energy. Some models suggest wormholes could masquerade as effects of dark matter or local gravitational anomalies. Studying irregularities in dark matter distribution, unusual stellar accelerations, or galactic cluster motions might hint at hidden tunnels shaping the universe's structure. Each of these signs alone is not proof, but combined, especially through long-term observations, they could provide a compelling argument for the existence of wormholes. For astronomers, it's like unraveling an invisible knot. Ordinary objects are visible, while the wormhole manifests only through subtle yet stable and repeatable indirect effects. Observing wormholes is therefore not just a search for an object, but an exploration of the very fabric of reality. Scientists look for patterns that violate conventional physics, and within these anomalies,
may lie a pathway through space and time. The future of humanity with wormholes. Wormholes remain at the boundary of science and imagination, yet even their theoretical existence reshapes our vision of humanity's future. If one day we can detect, stabilize, or travel through such tunnels, entirely new horizons in space exploration, understanding of time, and civilization's capabilities will open. 1. Scientific progress. Every step in studying wormholes reveals fundamental laws of physics, the nature of space-time, the properties of exotic matter, and quantum effects. Even theoretical modeling sparks new ideas in gravity, astrophysics, and quantum mechanics. Over time, these insights could yield unexpected applications, new energy sources, advanced materials, and technologies capable of transforming daily life. 2. Cosmic travel. Wormholes can make distances negligible. Instantaneous travel between galaxies would turn stars from unreachable points into potential sites for colonization and research. Humanity could observe the evolution of the universe in real time, access resources on distant planets, and create a network of corridors linking remote corners of space. 3. Impact on society and civilization. The emergence of wormholes will transform political, economic, and social structures. Control over instant transit portals would become a new form of power. Ethics and responsibility take center stage. Who decides where and when travel is allowed, and what historical or future consequences are acceptable? Legislators, philosophers, and scientists would face unique challenges. 4. Understanding time and history. Travel through wormholes could reveal time as a flexible structure. Observing the past or future within a tunnel may force a re-evaluation of causality, fate, and responsibility. Humanity will need to recognize that actions can have consequences beyond familiar temporal boundaries. 5. Global risks and limitations. Despite the allure, wormholes remain extremely unstable and dangerous. Any intervention could collapse a tunnel, produce catastrophic gravitational effects, or create time paradoxes. Future research must balance ambition with caution. Progress is impossible without understanding the potential hazards. And yet, the prospect of wormholes is inspiring. They represent the frontier of human knowledge and capability, the point where physics meets philosophy and imagination. Studying these phenomena promises not just discoveries, but a chance to rethink the very nature of travel, distance, time, and life itself. Ultimately, humanity's future with wormholes is one of extraordinary exploration and immense responsibility. We stand on the threshold of perceiving the universe not as a static stage, but as dynamic space-time, ready to reveal its secrets to those who approach with care and respect. Humanity could witness an era where the distant ceases to be unreachable, and time is no longer absolute, forever changing our understanding of our place in the cosmos.